Welcome to the second part of our course, EEE 341 Introduction to Communication Engineering. In this part, we will talk about different aspects of modulation technique and also some popular modulation techniques that we use. Before diving into the details, let us talk about two types of transmission, which are baseband transmission and passband transmission. So what is a baseband transmission technique? Let's imagine you and your friend is having a face-to-face conversation somewhere. What happens in that case is, you deliver a message to your friend, and that message is in form of some speech signal. That speech signal is transmitted by air from you to your friend. There is no intermediate block that converts your signal. This is what baseband transmission is. In the case of baseband transmission, the signal is transmitted in its raw form without any modification to it. But in the case of passband transmission, the signal is not transmitted in its raw version. Let's imagine you want to deliver a message to your friend who is not near you, maybe far apart from where you are now. In that case, simply yelling the message will not work. He or she will not listen to it. So there have to be some intermediate block which converts your signal and makes it more suitable for transmitting the signal over a long distance. That is the function of a modulator. We will talk about in the next portion. You can see from the visuals that in the case of baseband transmission, the signal is in original form and it has a frequency spectrum like this. Obviously, these are just hypothetical diagrams. This is actually not the Fourier transform of this signal. Let's imagine that this is the Fourier transform of this signal. So in the case of baseband transmission, they are transmitted in this raw form, and in time domain the transmitted signal looks like this, and in frequency domain the transmitted signal looks like this. But in the case of passband transmission, if we want to transmit the same signal, this may be converted to some other signal which looks like this, and in that case this signal will look like this in frequency domain. Let us know a bit more detail about baseband transmission. So what is baseband? Baseband is the frequency band of the original message signal from the source. Most baseband signals, such as audio and video, contain significant low frequency components, and the baseband bandwidth is equal to the highest frequency of the baseband signal. In the case of baseband transmission, here you can see a signal in its raw form is transmitted from the source to the listener. This signal is a baseband signal and has low frequency components. For example, in the case of human speech, the highest frequency may be 4 kHz. As you can see, in this path there is no modification block, so the signal is transmitted without any modification to its spectral components. One thing to note, low frequency components are more prone to interference and attenuation. That's why baseband transmission is not suitable for transmitting a signal over a long distance. It is better to transmit a baseband signal through coaxial cable, and not using wireless channel is recommended. Now let's do some experiment. Let's imagine in Brachy Cafe at lunch period, 3 people are trying to deliver 3 different messages to 3 different individuals. What will happen, do you think? They will talk at the same time, so their signals will be overlapping in time domain. So we cannot differentiate them in time, right? If it was the case where 3 people were delivering messages at 3 different time frames, then it could be possible to differentiate the signals in time domain. That is not possible because they're all delivering the message at the same time. So the other option is discriminating them in frequency domain. But the problem is, as you know, for human speech, bandwidth is limited from 0 to 4 kHz. So actually in frequency domain, these signals are also overlapping. Let's demonstrate it. Let's say this is our frequency axis. The message of the first signal for the first person is this. This is the spectrum of the first message. This is having the frequency spectrum from this to this. Maybe this is 4 kHz point. The next person has similar sort of bandwidth. Of course, the shape of the spectrum is different because the signal is different. But if you look at the bandwidth, then the bandwidth is similar. And the third one, again, similar bandwidth. So we cannot actually differentiate these 3 signals in time or frequency domain. This is the lacking of baseband transmission. If you do not make any change or modification to the spectral contents, as they are human speech, they will be overlapping in frequency domain, and we cannot actually differentiate which signal is meant for whom. So the problem is, for the baseband transmission, the signals are overlapping in both time and frequency domain, and thus we cannot differentiate them in time or frequency domain and it is very difficult for delivering a message successfully. Let's talk about passband transmission now. In the case of passband transmission, unlike baseband transmission, some change to spectral contents takes place. In the case of passband transmission, the baseband signal is modified with high frequency carriers, and the modulation process shifts the baseband signal to a higher frequency range. So in the case of passband transmission, the original signal from the source first reaches the modulator, and the modulator then changes the spectral components of the signal. Here you can see the difference between the input signal to the modulator and the output. The modulator introduces some adjustments to the spectral contents of the bandwidth. Here you can see the difference. In the case of original signal, there were only low frequency components, but in the output signal from the modulator, the signal is shifted to higher frequency. And then this modified signal reaches the listener. So what is the process of this modulation, how it is done? These things will be discussed later in the course, but for the time being, this idea is necessary that modulator changes the spectral shape of the signal, and it is useful for transmitting the signal over a long range. Now, this is the magic. Remember the previous spectrum where three people were talking simultaneously. In that case, there were similar shapes like this, and all the spectrums were stacked in the low frequency range, right? All of them were stacked in the same place. But now, as the modulation process is taking place, those spectrums are shifted to higher frequencies and shifted to different frequencies, most importantly. Even though they're still overlapping in time domain, these three signals are well differentiated in frequency domains. And now, as we will send these three signals simultaneously over a long distance, and the mixed signal will be received by the receiver can actually differentiate these three signals due to their frequency differences. We have already got a surface level idea of what modulation does. Now the question is, why is modulation necessary? Why it is so important to have passband transmission system? We will discuss some points of the significance of modulation process. This is the first one. The human speech is always limited to 4 kHz. The frequency of male speech, female speech, and also the speech from a baby may differentiate by some range in frequency domain, but they are always limited to this 4 kHz range. But we have a huge frequency range available. Let's say the radio frequency is some megahertz. We have megahertz level frequency available to us. So why should we use or only be limited to 4 kHz range? We have a large spectrum of frequency available. We should use it properly for increasing the capacity and the quality of communication. The main theme of modulation is to convert the low frequency signals and shift them to higher frequencies. That is what we have done in the modulation process. Previously, all these three spectrums were stacked in this low frequency region, but now, with the help of modulation process, we have shifted them to higher frequencies, and most importantly, different frequencies. All of them were previously in 0 frequency range. Their middle frequency or center frequency was 0 previously, but now with the help of modulation, we are transmitting this signal to F1 center frequency, this signal to F2 center frequency, and this signal to F3 center frequency. We are utilizing the frequency band carefully, and also as they are separated in frequency domain, they have some gap in between them. The receiver can actually distinguish between three distinct signals. So there are two parts of using modulation. The first one is the efficient use of the frequency band. We have a large frequency band and we are using it efficiently, not only being limited to the low frequency. And also, as we are transferring different signals to different frequencies, we are now enabling simultaneous transmissions of multiple users. Moving on. Another important aspect of modulation process is antenna length. To give you a heads up, antenna length is proportional to the wavelength. In the case of baseband transmission, let's say we are transmitting a signal with 1 kHz. What is the wavelength? You can calculate it from the formula C equal F lambda, and from that formula lambda is calculated to be 3 × 10 to the power 8 meter. If the antenna length is in the order of 1/4 of the wavelength, then in this case the antenna length will be 75,000 kilometers. Oh my god. Even I think Everest has a height of 7,000 kilometers. But in the case of passband transmission, we are actually transferring this signal from low frequency to a higher frequency range. Let's say we are modulating this low frequency signal with a signal of 100 megahertz. When the frequency is 100 megahertz, then the corresponding wavelength is only 3 meters.
and 3 meter means the antenna length will be just 0.75 kilometer. So with the help of modulation process, we have substantially decreased the height of the antenna. You can see the difference between these two pictures. This is the antenna used for baseband transmission, which is huge, and in the case of passband transmission, the antenna length is much favorable. Another significance of modulation is increasing the operating range. Let's say you are using baseband transmission system. In that case, the signal you are transmitting has low frequency, which implies that the power of the signal is low, because the power of a signal is proportional to the square of the frequency. So low frequency means low strength, and generally low strength signal will have shorter range to operate. But when you are modulating the signal with a high frequency carrier, then actually you are increasing the operating frequency, and increasing frequency will result in higher strength and thus longer operating range. So these were some importance of modulation process. To finish off, let me provide an analogy of what is modulation. For example, you have written a poem for someone on a piece of paper, and you want to deliver the poem, but you are too afraid of it, and you want to just throw it to your recipient. What will you do? Will you just throw the piece of paper in the air? No, you won't, because that piece of paper will not travel a long way to reach the desired person. What can you do instead? You can take a piece of rock, wrap the paper around the rock, and then you can throw that piece of rock, which is wrapped by the poem, to the person you want. This is actually very similar to modulation process. The piece of paper with the poem was the original signal, which was low frequency signal and didn't have the strength to travel a long way. But when you are wrapping the piece of rock with this paper, this is actually similar to modulating the signal with a high frequency carrier, and then that high frequency carrier or that rock will take the piece of paper with it. Same thing happens here. The high frequency carrier will take the low frequency signal with it and eventually will travel longer distance. So we are now in the last part of this lecture. We will conclude our discussion with the classification of modulation process. Basically, we have three types of modulation process. They are analog modulation, digital modulation, and pulse modulation. We will talk about these individual modulation techniques in this course. First of all, analog modulation. Analog modulation can be further divided into three types. First of all, amplitude modulation, then frequency modulation, and then phase modulation. Frequency modulation and phase modulation are collectively called angle modulation. So we have two types of analog modulation. First one is amplitude modulation, and then frequency and phase, which are called angle modulation. The first modulation technique we are going to talk about is amplitude modulation. And amplitude modulation is further divided into some types, such as double sideband modulation, single sideband modulation, vestigial sideband modulation, and quadrature amplitude modulation. These are very mouthful names. We will talk about the individual types of modulation techniques in details in this course. For amplitude modulation, we will spend quite a lot of time with double sideband modulation and single sideband modulation. That is all for this lecture. In the next lecture, we will start our discussion on amplitude modulation with double sideband modulation. Thank you.